you should think of it as adding value. So if you're doing some work to a workpiece, it should be value that the customer is willing to pay for. So over processing is waste. Okay. And that's something that we cover in quality, and we talk about it at length. But here it's something that you should still be at least aware of. It's not, quality doesn't happen in a vacuum kind of a thing. So a basic work holder. So a work holder at its core provides resistive force to whatever the workpiece is. Okay, and generally this is subtractive. It could be additive as well. So it's possible that you have some sort of additive process that actually applies pressure to the workpiece, but generally it's going to be subtractive. And the types of force you'll see, the typical ones are going to be the ones I have there: pneumatic, hydraulic, mechanical, magnetic, or electrical. So there are vacuum, which is, I guess, a type of pneumatic, and the general ones you're going to see are some type of mechanical with a pneumatic or hydraulic actuation. So if you've ever seen a Kurt Weiss, and you can Google that, K-U-R-T, Kurt Weiss. That's a very common machinist vise, and you could put a piece in there and then tighten the vise down and hold on to it. And there's an entire industry devoted to these things. Again, every lecture I'm going to say this because it's applicable, but if any one of these topics really interests you, you could delve into it, because each chapter in this book, the way it's broken up, is kind of a whole series unto itself. So with work holding, the possibilities are endless. If you went to a company website like Enerpac, I think it's spelled Enerpac, or Vectec, you could spend a lot of time on there and essentially see there's like an endless supply of different work holding methods. So the work holder purpose, the main purpose is that whenever you're cutting, from our cutting tool design talk, whenever you're actually trying to remove that chip, there are forces involved, and the reaction forces ultimately are supplied by the work holder. So if you have some sort of block, and bear with me on my drawing here, but you have some sort of block. Let's see here if we can do this like this. And the block, actually, let's get rid of all this. I don't have a lot of room here. That's okay. So you have your block here, and we had that tool that came down, and it kind of cuts along here. It cuts on two surfaces, right? And then it removes this material here. When that's occurring, when you're trying to remove that square of material here along that length, you need a reaction force. Okay, and you can think about this as, your book has a picture of wood being whittled. So if you think about it, you're holding a stick and then you got a knife in the other hand, and you're whittling the wood down. So instinctively, you have to provide some resistive force. And also, in the sense of machining, the workpiece is held by the work holder, usually in a very consistent way. So unlike the whittling example, where the piece of wood's kind of floating all over as your hand moves, the work holder is going to be supported by the machine and the table. And remember, we drew the little sewing machine looking example where you have this machine like this, and then you have the workpiece, and then you have the tool coming down. And you have this chain that goes from here all the way through to here, and that has to be very rigid. So that work holder is going to hold that workpiece very tightly and very rigidly relative to the tool. And all of those things are interconnected, and they need to be very precise in order to work. So if you think about it, when you put your work holder and your workpiece on the table, if they're not in the same place every time from part to part, then when you go to machine features into them, value added features, if their location moves, if their size is wrong, but that's one thing. If their location moves, that's a problem as well. And for those of you in my other classes there, you heard me mention that size and location thing again, right? That comes up again and again and again in manufacturing. Okay, so that's the basic purpose of a work holder. So the design considerations are, it has to keep the workpiece fixed relative to the machining operation. So what that means is wherever it gets bolted down on the table, it needs to more or less stay there. Okay, it can't move around while it's being machined. Just like if you were trying to cut something, if you were cutting tomatoes on your kitchen counter, if the tomatoes were rolling around while you were trying to slice them, you wouldn't do a very good job at it, right? You'd hold the tomato in one hand, and then you'd carefully hold a knife in your other hand, and then you would slice the tomato, right? So it's the same idea. So you need to hold the workpiece fixed relative to the machine. So there's zero velocity and there is zero translation or rotation from the workpiece to the machine. They're held relative fixed to one another. Okay. And also the work holder can't distort the workpiece and or damage it. So if you think about it, if you had some sort of soft piece of aluminum and you had some vise, we'll draw some vise jaws here. And this is going to be like a really, really lousy looking vise. But you'll get the idea. And we have there's some screw thread in there. And then here's your screw head. And then you have some sort of handle that you turn. And you rotate it. And that rotation creates some sort of translation in the jaws. And let's say you have some round piece in here. And this is some piece of stock. As you clamp those jaws down, you don't want to flatten. If you start with this round, I'm going to try to draw a circle here. If you start with it round, after you pinch it, you might get some flats on the side. And you may not want that. It may be distorted. Right? And then now you have some problem here. You have flats on the sides when in fact that's what you really want, is a nice round piece. So generally it doesn't damage or distort. Now there are cases where you can't help but distort the workpiece, and when you release the workpiece, its size changes. But if it's done in a way that it's elastically deformed, so it will go back, if it's consistent, you can control it. Okay, and that's a concept. You can write that down. If it's consistent, you can control it. It really doesn't matter what kind of problem it is. If it's consistent, and if you understand fundamentally what's causing the problem, then even if it's a problem, you can work with it usually, right? So if you're cutting parts and the measurement is consistently off by 0.010 of an inch, you can just make an adjustment and you'll be in. If the measurement bounces all over the place, now that's a different problem, right? That's harder to deal with because now we're not under control. So if we're in control and we're wrong, we can just correct. But if we're out of control, then we got a problem. Okay, it's like a life lesson. All right. And then the work holder has to repeat from tool to tool. So essentially, as you do a tool change and you bring a new tool in, you need to be able to come back down and do work, and the part cannot have moved. Okay, the new tool should be put exactly in the same place as the old tool relative to the workpiece. And then ultimately you want to be able to repeat from workpiece to workpiece. So, when you make a part, that's not it. You don't finish the part and then throw the machine in the trash and, that's it. You made one part and you're good. You're usually going to make a lot of parts. So, some things are just one-off jobs where you just do one or two. But, a lot of times you're going to do many pieces. So you plan on repeating the process, it would be nice if you could load it only one way and the workpiece would replace itself exactly the way it needs to be. Okay, and there's a lot of design work that goes into that. Anyone who has done machining knows that that's a difficult thing to do. It can be done, and it's done all the time, but there's a lot of thinking that needs to go into it. And then also, you need to be able to maintain your purchase on the workpiece until all your machining operations are complete. So if your machining operations are mid-process, and let's say you've cut away a lot of material essentially, and the load paths from the vise as you're gripping that little cylinder in our example there with our little cheesy vise I drew, if you machine away right through the center, if you think about this, so here, let me color it in so we can see here. Okay, so we have this little part. If you machined in half this part while you were holding it, what would happen? It would collapse, right? And now it wouldn't be tight in the vise anymore. So as you're machining this, you have to be careful that you don't, if you machine part of this out, let's say you machine this out, and then you machine a little bit more, you have to be careful. If you end up with a shell, you might crush it. So that's something to consider too. And sometimes that's a very real concern. And you have to very carefully think about where you actually hold on to your part and how hard you machine it. Meaning, how much material you remove. Your material removal rate can be too high to where you actually distort the part. Okay, so these are all things to consider when you're making a work holder. Okay, so locating and supporting. So the workpiece must be accurately located in the work holder. So, we talked about that already. You've got to put it in there, and you've got to be able to put it in there, the workpiece in the work holder, so that it's where you think it is. Okay. And then the cutting tool, when it comes in and starts its cutting, it needs to be relative to the workpiece the way you think it's going to be when you program it. Okay. Because if you think about it, when you're machining something, the way a CNC machine works, when you bolt the part or you bolt the work holder onto the table and then you bolt the part or you clamp the part into the work holder, if while it was machining a bolt came loose and it moved, the machine doesn't know that it moved, right? The machine's just going to keep running. Most machines don't have some active kind of detection to know that a part's moving. There are torque sensors and there are different things that can kind of check and see what's going on. But if you're engaged in a cut and suddenly you move translate the workpiece in a way that's not expected, the machine won't know. Then it will just make a bad part or crash or break something. So everything has to be held very precisely. Also, the locating points of the work holder have to be able to support that direction, the magnitude of the force. Okay, so if you think about it I'll just draw like a real simple simple fixture here. So we have two supports here, and we'll draw, this is like the table, and then here's our workpiece. Our workpiece is just sitting here. Okay, and let's say we have some sort of clamps that come down and they clamp and they hold the workpiece. Okay, this is good because the force from the clamp is transmitted directly into the support. Okay, because if we did it in the middle, we might have an instance where the part actually kind of bows, right? If we pinched it in the middle, we could bow the part. And even then, if we're drilling into the part, we're drilling into it and we're pushing on it really hard, we could actually distort the part. So we have to be careful to lay out the fixture, the work holder, and the machining process so that support is had and we don't get more deflection than we can handle. Now, there's always going to be some deflection. I don't know where you're watching this at, but if we're in the classroom, if we're all sitting in the classroom on the concrete floor having a discussion, we're actually deflecting the concrete floor. It's just a very, very small amount, right? There is strain, measurable strain, if we could measure that sensitively. But we don't fall through the floor, right? The floor hopefully holds us up. So there's always some deflection. It's just a matter of how much. And if it's plastic, or if it's not plastic, if that force gets applied and the part translates, the part moves, that's a problem. And also, you should design work holders so that you can rebuild them quickly in a production environment, if at all possible. And I'll talk about that more as a general concept going forward. But whenever you make a fixture, you ideally want a fixture that's easy to make and is cheap. Now, a lot of fixtures are quite expensive because of how precise they have to be and how complicated they can get. But you want to try to keep it simple and make it so that if something does break or needs to be rebuilt, that you have a controlled failure and not a catastrophic failure. So you don't want to have to rebuild the entire fixture. Maybe you want to just have it modular so you can just replace the part of the fixture that gets worn or damaged. Okay, and I'd encourage you to watch the video, that link. If you have your notes, you should have your notes open while you're following along with this. You can watch what machining crashes look like. And we can talk about that in more detail. It's kind of fun to watch. Okay, so the locator considerations. So with part locators, there are a whole host of things you need to be thinking about, especially if you're in a production environment. If you're in a job shop environment, these are still important. I mean, they're still very important, but especially if you're thinking about it with any sort of high production, or if the fixture is going to be around a long time, then these come up more. So especially like the first one, can the part be loaded and unloaded easily? So if it's a job shop environment and you have some sort of Kurt vise and you load the part and you have to indicate the part in, probe it or manually indicate it in, you can do that and that's fine. And you can make money doing that. But if you were going to do the exact same part, 50 times a day, and you thought you were going to make 50,000 parts, you would not want to do that every single time. You'd want to spend the money to design a fixture so you could just drop the part in and then clamp it and it would be repeatable. Okay. The other consideration is we've talked about, does the part distort on the locator? So when you pinch the part, are you crushing it or deflecting it in a way that you don't want to? Big thing is to know if your locators are commercially available. Because anything that's commercially available, so COTS, commercial off the shelf, is something that you're going to want to, so that's the concept of. So commercial off the shelf, okay? That's something that you're going to want to keep in mind. If it's a bit commercially available, try to use it. Anything can be made, and there's a great temptation when you got a bunch of CNC machines around to just haul off and start running them to make stuff. And there may be times where you need to do it, and it's totally appropriate. But if let's say your bread and butter is you're making, gearboxes for aircraft or something like that, you don't want to be in the business of making little rest buttons for machining fixtures, right? You want to buy those because you make money making gearboxes for aircraft. You don't make money making screws and nuts and bolts, right? You buy those. So that's something you're going to want to figure out. And then also, if you're doing some sort of fixture design and you're working with programmers, maybe you are the programmer, but if you're working with programs, you want to make sure that things like your cutters are going to clear your locators because you don't want to machine them off while you're machining, right? And then you want to try to figure out from the standpoint of looking at the part, do you have machine surfaces locating the part or cast surfaces? And if they are cast, can you adjust them? So, and depending on what the part is, sometimes you don't have to do that. But those are the kinds of questions you should ask if you were in a situation where you needed to design them. Okay, workpiece surfaces. So usually the workpiece is going to have a couple types of surfaces, and depending on the surface kind of governs how you're going to pick the locator. All right, and these are general rules of thumb. I'm not saying that, you know, you can't find a counterexample here. I'm just saying like broad brush rule of thumb here. So 3 types of workpiece surfaces. So the common ones are flat surfaces and cylindrical surfaces, you know, or some combination of that. So you have a flat surface on one side and you have a cylindrical surface around a radius on the other side. So those are the 2 kinds of things you're going to see a lot. You know, so you have the like a block like this, and then, you know, it has a hemispherical end. You know, I don't know what that part is, but let's say the part's like, you know, some part, and it's got sides round and the sides flat. You know, here it has some sort of radius R, and then it's got some sort of thickness here, T. So how would we locate that part? I don't know. It depends on what we're trying to do, but those are the kind of things you see. So then irregular surfaces, that's the next kind of category. And obviously I'm being somewhat facetious, most fun to deal with. So irregular surfaces are difficult to deal with. And there are different strategies for trying to work with them. And usually you see this if you have some sort of near net shaped part. So if you have a cast part or a forged part, that's where you see it most commonly. And then I would say after that, it's probably some sort of MIM part where there's a feature that you just have to have finished machined. You can't do it complete. So, because those can make all kinds of crazy cool shapes. And your locator types, you're going to usually have planar locator, which is what you use to locate a flat surface. And then you could have a concentric locator or a radial locator. Okay. And I would encourage you to leaf through your book, because again, I picked the book for a reason. It's really good and has a lot of really good examples here. Okay, but these are some locator types that you're going to see commonly. So, you know, what does this functionally look like? You know, you might have some sort of fixture. You know, let's say you have this surface here, and then you have some sort of flat rest buttons, and then you lay that part that we had in the other slide on it, and these surfaces right here are flat and they're planar, and you just lay the part and they're flat. They match up. They match up right here to the workpiece. Okay, so this area here, I'll color it in so we can see this is flat and this is flat. They're planar. That's it. Okay, and then maybe, but you say, but that part is just kind of sliding all over the place. That's true. So maybe there's a hole in it here, and maybe you have a pin that sticks out of the part, and the pin goes up through here, and now the part can spin on that pin, but that pin is like a concentric locator. Okay, and then maybe on this side, maybe there's another hole through here, and out of this rest button comes another smaller pin, and now that's your radial locator. So, you know, this is your number one, is these flat ones are number one. Okay, and then number two is this one here, and this is your concentric locator. And number three is this one, and this is your radial locator. So now from the top, I'll draw like a top view of this, just real rudimentary. And let's say it has, we'll say it has the 3 rest buttons underneath, and then it has a big hole in the middle, and one of these rest buttons has a hole through it. Okay. So, you know, and from the part standpoint, maybe the part just looks like this. The part just looks like that. Okay. And, you know, the part is flat, so the rest buttons sit here on the part. And then this is our concentric, and then this is our radio locator. And that's how we hold the block down. Okay. So that could be, and then, you know, I just made that up. That's just a very simple idea, but that's all it is. Basically, you're talking about little pads, little metal pads, and little pins to hold things. That's what it boils down to. So degrees of freedom. So we've talked about degrees of freedom a little bit, and in almost all of our classes, somehow degrees of freedom comes up. Okay, so you should familiarize yourself with that concept. And I'm not going to draw it or figure it out at length for you. I'm just going to mention it here because it's germane to the concept of restricting a part. If you look on page 99 of your book, figure, so go to page 99, you go to figure 410. There's a really good degrees of freedom kind of picture. So remember, you know, you pretend you have your smartphone floating in space. You know, the smartphone can rotate about its X, Y, and Z axes, and it can translate back and forth along all those axes as well. And that's where you get your movement from. Okay, so look that up and make sure you have a picture in your mind of how that's going to work. Okay. So the 3-2-1 method. So the 3-2-1 method is essentially the way that you can get all your degrees of freedom locked down. Okay, and your text has some really good picture examples. Okay, and I think they're figures. I think it's a continuation of what I just said. It was I think it was figure. I think it's 411, 12, and 13 are the different pictures, and you'll see it's just a series of pins. So you create a line or a plane, and then a line, and then a point, and you can get rid of all your degrees of freedom, and you'll have no more movement left. Now, we always are going to assume when we are restricting our degrees of freedom, if you have some sort of setup, you know, where I'm just going to draw a top-down view, and your book is going to show a picture of something similar to this. So you have 2 pins, and then you have 1 pin, and let's say underneath there are, you know, these other 3 pins. Okay, don't get too wrapped around the axle about my drawing. I know my drawings are not always the best, but you get the idea. So we have our workpiece, this is the workpiece. Okay, I'm going to call that WP for workpiece. Okay, so the workpiece now is held. It's on these 3 pins underneath of it, and that's our plane. And then the 2 pins are, you know, this pin, pin 1, and pin 2 are the pins that create the line, and then pin 3 here creates the point. And now it's held. We're always going to assume that there's some sort of clamp holding it down, right? So there's going to be a clamp there, and then there's going to be a clamp on top of it, pointing down. We'll draw that. What's the best way to draw that? I think we draw that with an X. So let's say we're holding it down. Okay, so it's clamped down in order to keep it from moving. But the reaction force is provided by those pins, and that's what actually restricts the movement. So the position of locators. So you need to position the locators. It's tricky when you do this because sometimes you find yourself in a situation where the locator to hold the workpiece is in the way of what you're trying to machine. So now you have to deal with that, and there are different strategies of dealing with that. So sometimes you might have multiple setups. Sometimes you have staged clamps, so that you have a clamp that clamps, you have multiple clamps that clamp down, and then the clamps release maybe in a hydraulic order, so that the part's always held down, but then the clamp gets out of the way just long enough for the machining, and then it comes back. Okay, I've done it multiple different ways, and sometimes you can just design the fixture around it. Oftentimes you can, but you don't want to have the clamp in the way of machining, and it has to hold it in a solid area. Right, so if you're machining some sort of beam or frame, and you have to have an area that's really thin, you may not be able to grab it because you might bend it or punch through the material actually. Okay. So the best parts too, by the way, as you can kind of guess from looking at your book and probably just thinking through this, is if you have mutually perpendicular planes on your part. So think about it. If I hand you a brick and I say, here, design a fixture for this, you can just open your book to page 100 and you can just copy the pins, the fixture they have, and then hold it down. It's very simple. But now if you have a part that looks more like a water bottle or something, or pick something that's not, a cube or a block or a parallelogram, now it gets trickier. It can get tricky fast. Okay. So if those mutually perpendicular planes are available in some way, take advantage of them, because it'll make your life a lot easier. Okay. And also the locators shouldn't be redundant. So whatever it takes to restrain the degrees of freedom is what you should use and no more. Right. So in our example we had where I had the pins coming through the part, through those holes, if we had 4 pins through the top, that wouldn't make sense, right? Because all 4 of those pins can't be engaged at the same time. And the concept for that is, think about when you went to a restaurant and you sat down at a table and it had 4 legs and the table rocks back and forth. So what do? You jam some, napkins under it or something. You fold them up so the table doesn't rock till you're out of there. Well, if you have a 3-legged stool, that'll never happen, right? Because all 3 legs will touch. But if you have 4 legs on a table, it's very difficult to get all 4 legs to touch at the same time, right? So if the table's big enough, it'll sag and bend and deflect until they touch. But if you have some sort of locating scheme where you have more than you need and they're redundant, some of them are not going to touch. And if they're not touching, they can only cause a problem. Okay, so don't make redundant locators. So locator details. So locators should have roughly 20 to 50% of the tolerance of the parts being made. That's a good rule of thumb. Okay, so meaning, the tolerance on the locators need to be flat. You need to be able to make it flat, basically, and flatter than what you're trying to machine. So if I had locators that were plus or minus 10 thousandths and I was just machining some wooden part that, didn't really matter, I guess, that would be fine. If maybe my part's to plus or minus a 1/16 of an inch or 32nd of an inch, I'm not going to notice that 10 thousandths, right? But if I'm machining a part to, plus or minus 2 thousandths, my locators should be in the hopefully maybe even to the tenths, okay, from one another, so that way I'm not causing an issue with the actual tolerance found in the locator. Okay, and also parts should be able to be loaded on the locator in only one way. So in lean, we would talk about that as being a poka-yoke, which basically means mistake proof. So if you poka-yoke something, you make it so that it can't be done wrong, right? So it's kind of like if you think about like an electrical socket or something, you can't plug it in wrong, right? If it has, let's say, 3 prongs, you can't plug it in upside down or sideways, or there's only one way that plug can go in, right? And why is it like that? Well, half the time it's like that to protect you, right? So you don't do it wrong and zap yourself or whatever. So you should think about that when you're machining things. You should try to make them so that there's only one way, and that one way is the right way. Okay, sometimes it's not easy to do that. A part can be loaded in upside down or something like that. But if you think about that, that's That's a big concept. Okay. And again, commercially available locators should be used if you can use them. Okay. So, if you go to the website like CarLane, you could go there. That's CARRLANE. Go to their website and search for locators, rest buttons, locator pins, things like that, and you'll get a feel for what's available and how much they cost and the different tolerances associated with them. So then locator types. So fixed locators, they're solid and they create an immovable datum structure. So fixed locators can look like, they can be integral. So if you have a fixture where you actually machine the locators into the fixture and then maybe you harden the whole fixture, that's one way of doing it. You can do that. And sometimes that's a good reason, but I would say don't do that unless there is a good reason, because the upside to them being integral is they're integral. The downside to them being integral is they're integral. So you can't change them easily without changing the whole fixture. So again, it depends on the application, but in general, they tend to be hard to use. So commercial pins, and commercial pins are just, if you go to that CarLane website, you'll see what I'm talking about. You can get all kinds of commercially available pins that can be used for radial or concentric locators. And then assembled locators. Assembled locators are things that are something maybe you bolt onto your fixture. So maybe it is custom made, but it's not actually integral to the fixture. You can take it apart. And then ground pins, you could use those for planar locators, radial or concentric locators, and they're easy to get. You can get them in different lengths. You can easily get them up to 2 inches long, and you can get them from probably, 30 thousandths all the way up to, 3/4 of an inch, pretty overnight kind of a thing, very quickly. Okay, and then V-type locator. So if you have some sort of fixture, and let's say your fixture looks like this, and you're going to put a round part into the fixture. What's the advantage of that? Well, the advantage of that is it'll center the part. So the center of the part is going to appear over the center line of the notch really well. Now the part can still rotate, so that could be a problem depending on what you're doing. Okay, and the height of the part from whatever spot, we'll say it's from the ground. Okay, the height can be affected by the diameter of the part, right? So if you have two parts, if you have part 1, and this is part 1, and then you have part 2, and let's say this is diameter 1, and this is diameter 2, and it's within your tolerance. When you put those parts into that V-notch, their centers are going to be at 2 different heights. You're going to get height 1, and you're going to get height 2, right? Height 1 for this one, and you're going to get height 2 for that one. So depending on what you're doing, that might actually be a problem. So you want to make sure you're aware of that. There's error there. Okay. So you want to make sure you're aware of that. But that's a V-type locator is a very common type of locator. Okay, a nesting setup. If you have a nest, essentially what that is if you have, let's say you have a plate, and then you have a cutout in the middle of the plate, and let's say you have some pins like this, and then you have your 1, 2, 3 pin, and then let me change the color and I'll draw a different color part in there. And now you take the part and you put the part and you drop it into the fixture. That's a nest. Now, depending on how you do the nest, it can hold the whole thing. Right, so this, we'd still have to have some clamps on it. And it's one of those things where you're still going to have to provide some sort of clamping. But a nest can be a good way to hold something. The downside with it is you have to be careful when you make nests because it'll trap chips and coolant. So remember, if you trap things on your locators, then you're going to have a problem. So let's say you have some sort of, I'll draw a part. So you have some sort of part. Maybe it's that same part we're already looking at. And then I'll draw the little locator buttons underneath of it. So here are your locator pins. If you have a locator pin here, and you have, let's say you have a little locator pin, and you have a tiny little chip on it, when you go to put the part on it, the part's not going to sit flat. That chip that gets in here is going to keep the part from sitting flat, and that's a problem. So if you have a nest, think about it. You have this little cup. It's basically you're making a spot for a puddle. Think of it that way. So usually, if you're going to make a fixture, a good way to think about it, the lean consultant way of talking about this would be, the lean way would be, you have Mount Fuji. Okay, and everything just rolls down Mount Fuji. Right? If you try to put something there, it'll just roll down the mountain. Okay, so you should think of your fixture in that way. So you want everything to just roll off of it. And if you think about it that way, it's actually kind of a good way to do it. So if all the dirt and the chips and the coolant and everything just kind of flow off of it automatically, you don't have to clean it. It's self-cleaning. So adjustable locators, you could have mechanical, pneumatic, or hydraulic. Those are the ones you see most commonly. And those are going to be used for processes where you can actually make adjustments. So if you have some sort of casting where you can have pretty good variation, you may find that you need the adjustable locators so that you can still keep your setup. Maybe you have a really good, slick, rigid setup, but depending on how the castings come in, it doesn't work. If you have some sort of adjustment, maybe you can still make it work. Okay, so if you see datum targets on a print, and the datum targets are movable datum targets, then you might think, okay, I need adjustable locators in my fixture to hold that. Okay, that's one way to think about that. And then internal locators. So internal locators, they're going to locate on the hole or a bore of a part, and usually they have a limited range of motion. So you can click on that link and look at that. I would say that internal locators are a locator of last resort. So unless you have a very specialized part, maybe you're doing some sort of like, I don't know, some big ring gear or something like that, where it's real obvious, like, oh yeah, we have to grab in the center, and it makes sense to. Usually, in my experience, internal locators are locators of last resort. If you're doing it, you should have a real good reason for that, because as cool as they are, they don't work very well. So they can be done, but they're usually much more difficult to make work properly. And you'll see that when you look at the actual examples, that they're quite complicated for what they do. So, and if you need them, they're fantastic, but you want to try to avoid them if at all possible, in my opinion. So diamond locators. So a diamond locator is just a pin, usually that has some sort of shape to it that looks like, oh, that's a bad drawing. That's the start of a really bad drawing. So let's do this. It's like more like this. We got like a round, got it round, and then it kind of comes out like this, and then it's like around here. So around here. Okay. And that is going to be part of a longer pin. So from the side, it would be like this. Okay. And you can look up diamond locators on Carlane's website, so please do that because my drawing is pretty terrible there. Okay, and floating locators, it's similar to a diamond locator and it'll correct for just small amounts of movement. So again, go to Carlane's website and you can look up pictures of those. They're actually pretty good, and it'll show you the differences. Okay, and you can click on the notes for whatever I have here for a good source. Oh yeah, Carlane. Okay. And then self-adjusting spring locators. Spring locators can be used to push things against more solid datum locators, and look at all these different types of locators on the Carlane website, because there's umpteen different types of them, and it doesn't make sense to show you all of them here. You need to spend time looking around at them. They're not very complicated. They're pretty straightforward, but you should look at them. But the spring type locators can be used to push a part against a datum locator when there's going to be a little bit of variability. So chip and burr issues. So we already talked about this, but chips and burrs create tons of scrap. Okay, so you don't want to make burrs in the first place, because a burr is a defect usually. No one says, "Can I get more burrs on that part?" Said no one ever, kind of a thing. So you want to try to avoid making burrs. Okay, and your fixture should be designed to be, as much as possible, self-cleaning in where it locates. So where the part actually touches those pins, if you go to your book on page 100, where you actually touch the part to the pins, you don't want a little chip in there. Because remember, if you have this metal chip and you have metal parts and you have metal locators, you're not going to crush that chip in there. That chip is it might get embedded in your part, which isn't good, but it's going to jack the part in the air a little bit, and then if it holds it up, it's kind of like tilted to one side. Now you're going to have some dimensional instability. Okay, and you'll see what I'm talking about. For those of you that are machinists already, you know what I'm talking about. But if you haven't done machining, that's okay. Just think about if you have that spot where you're trying to very carefully, within a few thousandths of an inch, place a part. If you have a chip that's maybe, we already talked about, if you're making a cut, let's say you're making your feed rate, your feed per tooth is 0.003 of an inch, or maybe let's say it's 1,000th of an inch. The chip is going to be usually about 1.5 thou thick, at least. So let's say you have that chip that's that thick and it's laying on your locator, it's going to push it up by at least that much, right? And that could be a lot. That could eat up all your tolerance right there. Okay, and then clamping principles. So your clamps need to provide enough force to counteract the cutting force imparted by the tool. And there's always should be like a little bit of a factor of safety, right? In case you have some sort of spike in the forces, something happens, you don't want the part to shoot out of the fixture. That could be bad. That's why if you look at the CNC machines as they're running, nowadays they're all inside enclosures. They're behind Lexan and sheet metal, and that's mostly to protect you. I mean, for one, it keeps the mess down because all the coolant and the chips spraying everywhere. You don't want them all over the shop floor, but it more is a safety issue, right? Because you don't want a part flying out of a poor fixture. And again, you want to clamp in such a way that you don't have any plastic deformation. If you have plastic deformation on the part, it's going to be a huge problem, because now your part's deformed, and probably not in the way you want it to be. Okay. And then the clamp should be located over the supports. I drew a picture of that earlier. When the clamp comes down, it should be in line with the part locator and not bow the part. Okay. And then another principle is auto clamping is usually preferred. So there are some clamps where an operator would have to lean in a machine and literally like turn a screw or turn a bolt with a wrench or something. You don't want to do that. If you're the engineer setting it up, you need to think about other people. And one thing is any repetitive motion you do can cause injury. And repetitive motion injuries are usually how you get hurt at work nowadays. Hopefully you don't get hurt at work. I mean, safety first, right? Not safety third, safety first. So you want to come home with all your fingers and toes and everything, and that's usually possible. But what sometimes happens is if you do a job for 8, 10 or 12 hours a day, and you're doing the same motion again and again, you can hurt your wrists or you can hurt your fingers, and it can cause a real degrade the quality of life of somebody. So especially when it comes to something like a clamp, if you have some sort of like screw clamp, the customer doesn't care how many times you screw and unscrew that clamp to get it clamped up, right? It's not really a value-added activity. So if possible, it should be done in an automatic way. And with modern control, with hydraulics and hydraulics and pneumatics that are electronically controlled, usually there's always an auto clamping solution. So if you're going to make 2 parts, if you're a job shop, then okay, fine. But if you're going to make 200 parts a day or a shift, you don't want to have to clamp those in and out every single time. That's really not preferred. And also, if you do have to do it manually, you might want to think about getting some sort of, impact wrench or something that is providing the torque versus your hand, rotating, because you just don't want to get injured. And repetitive motion injuries are big time. You see those injuries a lot because they're kind of hard to see, because if you do it once, it's not a big deal. It's only after it's a cumulative problem. If somebody's finger gets cut off, heaven forbid, it's a very in-your-face thing. It happens and it's terrible and it'll be dealt with. But a motion injury is something that comes up, kind of creeps up on you in a very surreptitious way. And so it's usually harder to anticipate or deal with. Actually, it's not hard to anticipate. You should be able to look at a motion and say, if someone does this 300 times a day, over an 8-hour shift, it's going to add up. But usually it's a harder sell for management. But if you're the engineer, you need to do what you can to push, being proactive about preventing that, because ultimately no one should get hurt at work, right? That's ridiculous. So, everyone should be safe at work. So that's something as engineers you should hold up highly. Okay. And then if a clamp looks complicated, because it's complicated, try to use a simple clamp, right? So sometimes clamping gets complicated or fixturing gets complicated, and you want to try to use the most simple thing as possible. So if it looks complicated, it is complicated, usually, okay? And complicated things are usually harder to keep running, all right? The clamps themselves shouldn't interfere with loading or unloading of parts. That might seem obvious to you, but I have definitely seen fixtures that when they were designed and put together could not be loaded, or once a part was in them, the part couldn't get out because the clamps just get in the way. So it's one of those things that seems obvious, but it needs to be checked up on. It's not given that it will happen. So, and then clamps should be able to be activated while someone is loading or unloading a part. So what that means is essentially you might have a part where you need to hold the part and load it in and then activate it maybe in sequence. So not always, I say this, but I should add, maybe like a with caution. So sometimes parts, ideally you don't have to activate it while someone is loading or unloading the part, but sometimes that's something that has to be done, and I see that frankly quite a lot. But there are ways to do it safely. There are plenty of ways to do it where there's either a clearance or there's some sort of two-hand touch operation, so someone can actually get their hand in there, but they have the machine open and maybe they're loading a sequence of parts, and they need to be able to put the part in and then clamp that part and then move to the next part without getting out of the machine. So, or without the machine doors closing. So usually I would say they should be able to be activated that way, but again, it's with caution. And if you use proper precautions, it shouldn't be a problem. So the clamping setup should be able to account for any tolerance variation of the part being processed. So again, if you have those adjustable locators and you have cast parts, it should be no issue. So last thing is tool forces. So the tool force is the force that the tool imparts to the workpiece, and the clamp has to resist that. Okay. And you essentially need to restrain against the direction that the force is being input, right? So if you're drilling and you're pushing down, the table can't get pushed through the floor, kind of a thing, or the part shouldn't bend, okay? And the amount of force that is imparted to the workpiece is directly proportional to the feeds and speeds, okay? And each type of operation has kind of general forces that go along with it. So what I mean by that is, if you're milling, you're going to have tangential forces and side forces. If you're drilling, your forces are going to be parallel with the spindle, and so on. And so you need to think about how those forces are being generated by the process so that you can accommodate them and design for them. Okay. And then the cutting forces themselves, usually the best way to look them up is there's been a lot of testing to calculate what these forces are, and they should be looked up in tables. So given the material and the removal rate, you should be able to back out what an applicable force is, and that's kind of how you would go about at least getting a ballpark idea of how much force is going to be applied to that part. Okay, so this is work holding concepts. If you have any questions, call, text, or email me. Please read your book, this chapter that goes along with this topic and the lecture in class. And if you have any questions, please reach out to me. Thank you.